Good.
Okay, Terry, please.
Professor Ye, would you like to say something before the lecture?
Should I just start, Jane, or do you want to say something first?
I think you can start now.
Okay, I'll just start now. This is the third lecture, and it's going to be devoted to subgradients and optimality conditions. So, as always, I am trying to put the perspective of this, that there are origins in classical analysis and, of course, convex analysis in what I'm going to present. But I want to look at classical analysis from a point of view that is not usually described, although we see some of it in elementary calculus. So, for example, when we learn the calculus of a function on the real line, and we are told about differentiability, we are given a geometric picture of differentiability in that you can imagine my picture here for a moment as being one-dimensional, that the derivative is the slope of a tangent line. The slope of a tangent line, or the infinitesimal, gives the derivative. So there's some geometric thing there. We're never really told about the normal. But now let's think of a function on Rn. And so its graph is in a space of one dimension higher. So there's some kind of hypersurface. Let's think of it as a hypersurface. Then as a smooth manifold, we have the geometry of differential geometry. And in differential geometry, there's a linear subspace that's a tangent space, and a linear subspace that's a normal space. And of course, the theory of differential manifolds elaborates on all this. But for our purposes here, we're just in Rn, and the tangent space is like a hyperplane that's tangent to the graph at this point, and then its orthogonal complement, which is just one-dimensional, is a line, and that's the line of normals at this point. But how does that relate to differentiability in this higher sense? So we have some idea in a one dimension, but many people don't think about what it means in higher dimensions. So in higher dimensions, it's quite clear that the tangent space corresponds to the directional derivatives of the function. And giving it's a linear function. Well, here, as always, it's floating. So although the tangent space and the normal space are subspaces, in which case this point would be like the origin. We have floated those spaces over here to be at this point. And anyway, this is somehow giving the directional derivatives of the function. And then but then what is the formula for a directional derivative? You could see by looking at the formula for a directional derivative in terms of the gradient that the gradient is actually the vector you get that's in the normal cone here when you move down to the -1 level. The vertical coordinate is -1, and then that vector will give you the gradient. So as I say right here, the tangent space at this point is the hyperplane giving this thing the directional derivatives, where it's the linear function with a gradient, and a normal space, which is local to that, corresponds to this gradient, and we have this local linearization in which there's a little O term. I have that the function is equal to this linear function plus an error term of this classical sort. Here I put double bars. I've been trying in general to be consistent, and when I use the Euclidean norm, I put single bars instead of double bars. So anyway, we could recover from this geometry, we can recover the gradient of the function as the unique vector v, for which v and -1 paired together belongs to this normal cone to the graph. So that's a geometric insight that will carry us a long way, because this propagates into the next case where we're looking at convex analysis. And convex analysis, we understand, departs from the classical analysis in that we focus now on the epigraph instead of on the graph. And the epigraph of a convex function is a convex set. So at a certain point here, this is a point in where on the boundary of the epigraph, since it's the value of the function, I have, instead of those subspaces, I have the tangent cone and I have the normal cone. These are closed convex cones. And this tangent cone, what makes an epigraph? A set in this product space is an epigraph if you look at each vertical line, it intersects it in a closed interval that's unbounded above. All right, now if you look at the set above, at this tangent cone, it's actually also an epigraph. It's an epigraph of a function. What is that function? That is what the directional derivative function that we get in convex analysis in place of the classical linearization. And then again, we'd have this -1 thing. We look at the vectors v that are at -1 level that are in this normal cone, and they turn out to be exactly the vectors that are at the subgradients of this. And because this condition on the normal cone corresponds exactly to this inequality that we have used for defining a subgradient. But a special thing when we get to an epigraph is we might also have to look at horizontal normals. So for example, here the epigraph is closed if this is lower semi-continuous. It has a whole boundary up here. It has at all these points, it has horizontal normals. We don't care about those normals really, but we do care about the horizontal normals that will be at points where we have the function value. And those will have a special meaning later. But for now, in our case of convexity, they turn out to be simply the normals to the effective domain. The effective domain is the projection down here of the epigraph. So they're just the normal vectors to the, but later on, it's important that we don't just get the domain and we get something else called a horizon vector. All right, now we get to the basics of variational analysis in this situation, where we try to generalize these ideas to epigraphs that are not supposed to be smooth manifolds and are not convex sets. They're just, we would like them to be, and we can have them be just closed sets, epigraphs that are just closed. So we have this notation here. It's all in the book. I just repeat it here. I use epi for the function and dom for the effective domain. And we see the geometry here. The domain is the projection of it. And the nice little fact of geometry is that the epigraph is a closed set if and only if this function f has a classical condition called lower semi-continuity, which corresponds to the level sets of this kind being closed. And I also want to use a notation of a function as proper. In general, a function that I'm dealing with could take on both plus infinity and minus infinity, but I call it proper, as in convex analysis, if it doesn't take on minus infinity, and it somewhere takes, it has a finite value. It's not the constant function plus infinity, which means geometrically that the epigraph and the domain are non-empty, and the epigraph does not contain any entire vertical line. All right, now here are the main features we're going to encounter. We're going to have subderivatives and subgradients. The subderivatives will be associated with tangent cones to the epigraph, and subgradients are associated to normal cones to the epigraph. And then, as in the variational geometry, there were two kinds of tangents and two kinds of normals. So that's regular and general. So that's going to be reflected by different kinds of subderivatives and subgradients. And they will coincide when we have variational regularity. And variational regularity of this epigraph is what will be called variational regularity of the function f. But there's also something special, as I suggested. There are horizontal normals and horizontal subgradients. These are called horizon subgradients, and they're not just normals to the effective domain. But what are they and why are they important? They're important because they are the essential ingredients that support rules for subdifferential calculus, all these formulas that we need to make this subject be helpful. We have to be able to calculate all these things, and that's where those come in. Now, looking at subderivatives in general, the subderivative in general, which just corresponds to the tangent cone of the epigraph, I have this notation where I use this df of bar x. This is a function in itself that depends on x bar, a function depending on x bar. And then its values at w, I look at this way. And they are taken by a limit, just as in classical differential directional derivatives. However, it's a one-sided limit. We're just going to look in general at the lower limit, the lim inf. And furthermore, we don't just do it directly on a line. We have to do it with the direction varying, because otherwise we can't capture curvature or feasible sets and things like that. As we saw earlier with a tangent cone, we have to look not just along lines as in convex analysis. So this gives the general thing which called a subderivative, the subderivative of the function at this point. And what is its epigraph is this tangent cone. So this is itself a lower semi-continuous function. But then there's also the regular one where I look instead at the regular tangent cone. And in this case, it will, I drew here a function. It's supposed to be here. It's hard to draw, of course. Infinitely many little bumps going in here, kind of examples we see here. And but there's a jump. The function isn't even continuous at this point. It's discontinuous, has a jump. Nonetheless, it has at this point a regular tangent cone, and the epigraph of that is this gives me the actually, this is just a tangent cone. This isn't the regular thing. Anyway, the regular subderivatives, I'm not going to show you a picture of it out of lack of time. The regular subderivatives are given by the regular tangent cone. We'll see it in some specific later. Right, then with subgradients, carry this all over. We have the regular subgradients indicated with a hat. And they are given by this compromise between the classical formula and the convex analysis formula. The compromise has the little o term of the classical formula, but it replaces the equation of the classical formula by an inequality, whereas the convex case doesn't have this little error term. These are then the general subgradients, which are obtained by taking limits from nearby points. And as we take the limits of subgradients from nearby points, we have to pay attention to the function value. And the need for that is explained in this picture. I'm looking at, say, the subgradients at the origin here, and I'm clearly interested only in properties that would depend on the epigraph here. But if I don't pay attention to the value of the function, I might also be looking at things around here which are not essential. So this is a bit of a troublesome complication, but because we don't want to assume functions are continuous, they're only lower semi-continuous, we do need to take that into account. Then there are the horizon subgradients. So those are the ones that are defined in a similar way by taking limits, except we take limits where the length of the vector would go to infinity, but we call that length with some factor, and we get a finite number. So these turn out then to have the following geometric significance, which is of course the aim of this whole thing. That this is supposed to turn out to be variational geometry as applied to epigraph, and it is. So for simplicity, if we denote the epigraph by E, then we have that the regular subgradients are obtained from the regular normal cone to the epigraph, the general subgradients from the general cone, and then the horizon subgradients from this formula. And then we see illustrations in this picture of how it could work out in different ways. So at this point, for example, there are two subgradients, and the intermediate ones are not there. At this point, there are these limiting ones, and we have a whole interval in this picture of subgradients. Which in some places, of course, you could have a unique subgradient. And I'm not looking at the subgradients along this boundary. They all have to do at points where on the graph of the function. And let me repeat again that, well, maybe I'll go ahead again to this next picture. Well, yeah, no, I have to say this first. I'm going to come in a moment to the main interaction between all these different concepts. But I wanted to say something more first about horizon subgradients. They're connected with Lipschitz continuity. So let's remember that a function is locally Lipschitz continuous around a point x, if only if there's a way of estimating the difference between function values by the difference between points with some Lipschitz constant. And that holds for all points in some neighborhood of this x. And that's an important property that has long played a big role in the subject. And in Francis Clark's work, he started with Lipschitz continuous functions and defined things in those terms, and then went on to at other levels to what all the other functions did. But how does Lipschitz continuity fit into this? Here's a very dramatic criterion, it seems to me. What property of a, we just have a lower semi-continuous function is all we know, and we have a point x bar where it's finite. What property of f characterizes, that you could use as a calculation, could characterize that this function is locally Lipschitz on a neighborhood of x bar? And the answer is it's the subgradient condition that the only horizon subgradient is the zero subgradient at that point. Now that maybe seem very abstract. How are you going to draw a picture and find a horizon subgradient? It's important because there will be a calculus of subgradients, and part of the calculus will include the calculus of horizon subgradients. So we can start, as in classical calculus, with basic primitive ingredients and build up formulas that will tell us what these things are, and therefore give us a criterion that can be verified. And a further thing is, this is exactly the case where the subgradient set itself is both non-empty and bounded. It's possible to have a non-zero subgradient at a point where there's a horizon subgradient, a point where there's no other subgradient because it might be the function is too steep there for a subgradient. So anyway, you have this triple characterization, which really shows the power of some basic idea. And right, and then there are the regular subderivatives in this case. So they have a much simpler formula. For the regular subderivatives in this case, I didn't give you a formula last time because it's complicated. I just told you that the epigraph of it was the regular tangent cone to the epigraph. But it's given in this case by a simple lim sup formula. So you could imagine that you fix the x and you just take a lim sup. You could take, let's just drop down here for a moment. So in the case of a Lipschitz function, when I take the general subderivative, I don't have to have the convergence of w prime to w because Lipschitz continuity allows me to keep the direction fixed. So this thing is just like a regular directional derivative, except that it's a lim inf instead of a limit. But in the regular subderivative, it still involves a limit, but it's not necessarily the limit in the direction, but is a limit at nearby points. So this emphasizes again that this regularity, as in the sense we're describing it, has to do with some sort of local stability. So it's giving kind of an upper bound, no matter what point you are nearby. This an upper bound to this would give an upper bound to difference quotients at all points nearby. Okay, now we get to the benefits. Well, maybe I still want to say something. Maybe I'll go back for a moment. I just wanted to point out again that the big difference in all of this came when I was working earlier on this theory with Francis Clark. We were always taking the convex hull. And basically what we were doing was, instead of taking just the normal cone at any of these points, say at this point, not just taking the normal cone, we were taking the closed convex hull of the normal cone as described here. The closed convex hull, and that way, this would all be filled in and I would get a set, a convex set. So, and then the subgradient set would always be convex. And, but by taking, to understand here's a good point right here. To understand this convex hull, the closed normal cone here, the convex hull of it, if you're taking the convexification of, then this horizontal aspect is already included. But if you don't take the convexification, then the horizontal thing may be missing. Let me just try to think of well, I don't have a picture for you. I should have had a picture in here, but I don't have a picture, but it's possible that you can have the normal cone is non-convex, and that somehow the closure of the finite part, the closure, it's possible that the closure of this set does not include this set. In the convex case, the closure of this does include that, but otherwise not. So anyway, this made, because in what I saw, what Boris Bordamovich was doing with the convexification, I didn't see the evidence for the horizon subgradients. I resisted this a long time because I thought that the horizon subgradients were essential to a calculus. But then later, it all got reconciled. And anyway, now it's so important that we do not do this convexification. Now, all that is unnecessary in the presence of variational regularity. This is where the epigraph is variationally regular at the point in question. And that means that every subgradient is regular. All the subgradients in this set are regular. And it also corresponds to the fact that all these different directional derivatives coincide. That is the general one with the regular or Clark directional derivative, and it also corresponds simply with taking a limit and therefore with a classical one-sided derivative. They all agree in the presence of this, and as in the case of a convex function, for example. And then you have this lovely dual formula that generalizes the classical formula. The classical formula for directional derivative says that the directional derivative function is a linear function associated with a gradient. And here in this subject, at least for under variational regularity, we have this basically that this directional, the subderivative function is the support function of the convex set that's giving you the subgradients, which is a compact convex set. And furthermore, we have the fact that this subgradient set then is it's a singleton if and only if F has a property called strict differentiability, which I won't describe here. But anyway, it all fits together. The point is all these things fit together in a beautiful way. Now, we get to another feature of variational analysis, also in convex analysis, which I think is very extremely useful, and it doesn't exist in classical analysis. It exists in a way. It's that the way that we identify sets with functions. So it's true that in classical analysis, there's a way of identifying sets and functions. For example, in integration theory, you identify a set with what's called, well, I forget what it is. Anyway, it's the function that's 1 on the set and 0 outside the set. But we identify functions with their indicators. And the sets that are closed are those that have closed indicator functions. The convex ones have convex indicator functions too. And so now we could apply the theory of subgradients to the indicator functions. And of course, it all works out. That is, the subgradients of the indicator function are the same as subgradient as horizontal subgradients of it, and they give the normal cone. And the regular subgradients give the regular normal cone. And the directional derivative function for the subderivative function for indicator is the indicator of the tangent cone, and so forth with the normal version. And likewise, the variational regularity of the indicator corresponds to the variational regularity of the set. Now that's kind of like obvious and trivial, but there's something much more important to it than is shown, at least if we treat it right, because it shows that every result that we have about functions can tell us something about sets. And in second order theory, that will be especially important. But to get there, we notice that up till now, when I discussed the normal cone at a point X, it always meant that X was in the set C. And I still do mean that. But I want to I want to extend this as a mapping. So this would be a set value mapping that's only defined on the set C. But I wanted to extend this as a set value mapping on the whole space by taking its values to be empty when X isn't in the set C, because then I get this normal cone mapping on the whole space whose effective domain is the set C. And then we can state that this formula, the normal cone at C equals the indicator at the set subgradients set at every set X. And this has some rather really important and valuable examples. For instance, if the set is a closed convex cone, then you have the fact that the normals to that, this is in the subgradients, are given by, there's this duality in here. And so the normal cone mapping to the polar cone is the inverse of the normal cone mapping to K. You can't say that without making this distinction. And then later, when we want to study second order aspects of the set C, we can study, second derivatives of the directional derivative function, second derivatives of the indicator function will have something to do with second order properties of the set C. And now let's get into optimality. So we have the generalization of Fermat's rule. Fermat's rule is, I suppose, goes back to Fermat, a Frenchman of the 16th or 17th century, I believe, who noticed, or is said to have noticed, that if you look at a function of a real variable and you look at where it has a maximum, that there's something about the slope being 0. So the generalization of that, as we already know, well, a simple generalization that we just noticed here is that if 0 is a regular subgradient, if you have a local minimum, then in particular, 0 is a regular subgradient of the function at x bar. And since it's a regular subgradient, then in particular, it's a general subgradient. So we have then that this would be a necessary condition. Local minimum necessary condition is that 0 should be a subgradient. Well, why don't I emphasize this condition, which is stronger? I've already indicated in the previous lecture that being a sharper condition is not necessarily better for applicability, because the question is, can you calculate this condition? And there isn't a very good calculus of this condition, except in the case where the regular normals are all the general normals. This condition does have a good calculus, right? So now here we are minimizing, and in this illustration, I want to minimize a smooth function over the closed set C. And we already know that this could be viewed as minimizing the sum of this function f and the indicator of C. So here's a formula where we have the sum, and we want to calculate this thing. So I have to take the subgradients of the sum of two functions. So we need a rule for the sum of two functions. And here's the rule. It involves a constraint qualification. There's all these conditions, and indeed the constraint qualification involves the horizon cones. There's horizon subgradients for these two functions. There shouldn't be any vector in this horizon cone whose negative is in this horizon cone. No non-zero vector should be in this one with its negative in that one. So under that constraint qualification, then we get this inequality, I'm sorry. And then what's missing, what I could state more about here, but there's no place to write it all because there's only so much space here, is that there's also a side of this that computes the horizon cones of this new function, and the condition under which, if we have variational regularity, then we have an equation. And you remember here that this formula would mean that every subgradient can be represented as a sum of a V1 in this one and a V2 in this set. So now if we apply it to this case where we want to calculate the subgradients of this particular sum, we have a lot of special features. Because this function f0 is differentiable, its subgradient set is a singleton at this point. And because it's Lipschitz continuous locally, its horizon vectors set is just the 0 set. So that's going to make it, all this will be satisfied then. There can't be any non-zero. And then in the case of the indicator function, we have, just as we said here, we have the normal cone at that point. And so all the conditions are satisfied, and we include that this is included in the sum of these two sets. And that means that this condition has been specialized into this necessary condition. So it's a necessary condition that we already perceived in some ways, but out of the theory of regular normals to this set. But anyway, it's a necessary condition, and what's nice here is it shows how it comes from the calculus, and there are many other things you could do with this calculus. Here, for example, is another example of what we can do, which is more complicated, that we can bring in Lagrange multipliers to study this. So in this case, I'm going to build on this condition by specializing the set C. So I'm going to assume now that the set C is given by a condition where this vector of C1 function should belong to a set D. But for the purpose of example, I'm going to specialize the set D to be the non-positive orthont. So that means that this constraint system is just a system of inequality constraints. These M functions should all be less than or equal 0 for this a point X to belong to this set C. And my aim then is to apply the formula for the normal cone that was derived in the last lecture for this kind of set C. And that formula for the normal cone used the normal cone to this set D at this point. But now we have a very special set D. It's this non-positive orthont. So we need to know what is the normal cone to that orthont. Now, you remember that when we deal with a constraint system with inequality constraints, and we end up looking with Lagrange multipliers at complementary slackness. The multipliers that are associated with inequality constraints have to satisfy this condition S, that they're non-negative if the constraint is active, but they have to be 0 if the constraint is inactive. Complementary slackness. And this is exactly the condition. This exactly describes the normal cone. So this is a really good insight. So all that stuff about, I don't know, any of you have worked in optimization and you write papers, and many times you have to write down the complementary slackness conditions, and they're sort of always a bit of a complicated annoyance. But there's a simple way of looking at it. That is simply, it's just the normal cone condition for this particular kind of set. But that also tells us that we can deal with many other sets. You want to know what should be Lagrange multipliers in case you have some other kind of set? Well, that's what it is here. Suppose you're dealing with the Lorentz cone and second order programming. Suppose you're actually working with matrices and you're looking at the positive semi-definite cone. And it's just a matter of figuring out what the normal vectors are to that. And then, by the way, I gave a normal cone rule a little earlier with duality that exactly would come into play in this situation. So going back again now to this particular, I had a result about the normals to the set C. And that result had a constraint qualification. So here's the constraint qualification. In general, it was that the only y that if I look at the multiplier vectors y that could give this kind of condition as a linear combination, there is no such, except for the 0 multipliers, there is no such multiplier vector in that set. But that set is now identified with complementary slackness. So it would say there's something like that if I look at the vector satisfying the complementary slackness condition at this point, there's no such combination that will make this be 0 except for the 0 multiplier. So it's very similar to linear independence condition, which would be exactly what I would have if instead of I took inequalities, I would simply take equations. So then this would have turned out to be linear independence. All right, anyway, under that constraint qualification, Q, the vectors that are in the normal cone are exactly the ones such that, because I can apply that formula now, that there exists a multiplier vector y bar that satisfies complementary slackness and makes that sum equal 0. So these are the Karush-Kuhn-Tucker conditions for this classical problem. And then it comes out, and we state it in the more normal way here, as a necessary condition that under that constraint qualification, which is there are many ways to say it, it's classical, but it also coincides with Mangasarian and Fromovitz constraint qualification. It's in the dual form. That the local optimality of an X that in this case, this nonlinear programming case, entails the existence of those multipliers giving this condition. Now things don't end here because, as you know, in classical theory, then we pass to the Lagrangian function. Now, I don't really have much time. I have a little time to talk about Lagrangian function later, but that really plays a much bigger role in the end, but involves some kind of convex duality in defining the augmented Lagrangian. And that has to be left for later. But we can ask then, what about second order conditions? So far, I have gotten into describing first order conditions and even how you can get them with Lagrange multipliers. What then would we want after that? So if I'm thinking then and I'm minimizing a function over Rn, and I know the first order condition that 0 should be a subgradient. And now I know that to characterize a local minimum, there'll be something more. But I want to be very clear that my goal is not necessarily just to characterize as closely as possible all the extra conditions that would mean that I have a local minimum. I could just write down the condition for a local minimum if it comes to that. What I want to know is I want to emphasize the word here, help. What may help to characterize it? But I mean help. So what is the purpose to be served by this? What kind of help is it that you're looking for? And here I like to explain that the really different outlook in optimality conditions from the traditional outlook to the modern outlook we have in optimization. And it's interesting to think of why this is true. So in the traditional outlook, which is the one we learn in elementary calculus, that what we're trying to do is eliminate as far as possible. So we look at, in the classical case, it would be the gradient, but we have a bunch of candidates. The points that satisfy this condition, the first order condition, we can think of as candidates for optimality and for being a local minimum, but some of them may not be a local minimum. So what we want to do is find conditions that eliminate conditions on the function f, some derivatives or something, which eliminate conditions that satisfy the first one, candidates that satisfy the first condition, but are not happen to be a local minimum. Those are false candidates. But that's not really the purpose of second order optimality today. Because what is it that we look at today? What we're looking at, we want the kinds of properties. They shouldn't be weird, unusual properties. They should be rather typical properties that can be expected rather generally and maybe verified in many, many cases. We're looking for properties of a local minimizer X bar that help you find it with a numerical method. And I think this makes a really big difference between these two outlooks, because in the classical, what's a little hidden in this classical outlook is you imagine that you know these candidates. And we've all worked in elementary optimization, for example, in one-dimensional calculus, where we've looked at where the first derivative was 0, we found some candidates, and then we eliminated the ones that didn't give a minimum by looking at the second order condition. But that depends on actually knowing the candidates. How do you know the points that are in the set? But in the modern world, we're dealing with large problems. We have a problem in a million dimensions. How are we going to look at all these points? We'll have to use a computer. A computer will have to write all these points down. But computers compute things inaccurately. There are always errors. So the whole idea that we even have these false candidates is wrong from a modern point of view of optimization, where our problems aren't just one or two dimensional. Even solving the first order conditions requires computation. So what we need is to understand the things in a way that will promote numerical methods. So if we're dealing with, of course, then that also means that whatever second order conditions we look at, they have to be reasonable. Otherwise, we're not going to be able to use a numerical method without having some expectation that the condition could be satisfied in many cases anyway. So it's a completely different outlook. So that leads us then to second order variational analysis, and I'll be able to get to some of that in the next two talks. Second order analysis will involve second order subderivatives of the function f, subderivatives, but also there's a second way of looking at it, because in some way the subgradient mapping of a function is already a first derivative. So then we could look at derivatives of that, but that would involve graphical derivatives. So roughly graphical derivatives are what we're going to get by applying variational geometry to the graph of a set valued mapping, like the subgradient mapping. And interestingly, something more comes in about monotonicity properties of the subgradient mapping, even local properties, and that turns out to be quite an intriguing topic in second order analysis. So this is the end of my lecture for today. Today I am ending early enough, except for discussing a little bit here about the further study. So for the most part, the material in this particular lecture is from chapter 8 of the book Convex Analysis. It seems pretty far into that book if you just want to learn about subgradients. But it's inevitable with a book that there's so many ways to write a book, let me just say. If you want to skip ahead to variational analysis, you can go more or less directly from chapter 6 to chapter 8 without looking at chapter 7 yet. It'll come in later. And you can skip chapter, and then, of course, how did you get to chapter 6? You were able to skip chapters 3, 4, and 5 for the most part. So just basically from chapter 1 to chapter 6 to chapter 8, something like that. All right, now, as I was about to say, second order variational analysis and sufficient conditions for local optimality is an active research subject. And I'm very much involved. I'm involved in several things, as always, but my main excitement at the moment is working in second order optimality conditions and also the relation to some decomposition methods that I'm also working on. And a lot of that in the variational analysis book is in chapter 13 of that book, but that book was finished, now it's hard to imagine that, but that book was finished, 23, 24 years ago. And it was finished well in 1997, so 24 years ago, although it didn't come out until the end of 1997 with a 1998 date on it. But there's a lot I won't be able to cover, but I hope to explain some of the interesting parts of the second order analysis in the next couple of lectures. Okay, that's the end. Thank you. Okay, Jay?
Maybe he cannot hear you.
Yep.
Yeah, I think maybe she cannot hear you.
Sorry.
Yeah, she's back.
Sorry.
Yeah, okay.
I forgot to turn on. Okay. There was a message from Jean. He said that because there is another Chinese live streaming, so the total participant yesterday was over 300. just
Oh, that's interesting.
yeah, because not
I'm really
everyone.
glad to be able.
Yeah.
I want to thank you so much for this opportunity because I love to explain this, and the way I'm explaining it is a particular. Other people can explain the subject. You could, Boris Marhorish can, but I have my own way of explaining it, and in some way, maybe I have the longer historical knowledge too. So it's such a wonderful opportunity for me to explain that, and I'm very so happy that there's so many people listening. Thanks for that information, Gene.
Yeah, and after that they were posted in Chinese, like Chinese YouTube, and there will be more people watching it. So
That's right. That's right.
yeah, it will be staying there, and people will go watching it. It's really it's a great opportunity for us to listen to your talk. I will listen more than once. Because you have worked in this field for 60 years, right? And still, you still have new ideas. It's amazing. I just totally enjoy it.
Yes, it's interesting. My first work on my dissertation, where I was working on starting with all the stuff with convex analysis and duality and subgradients, this was in the winter of 61 to 62. So this is exactly 60 years ago.
Yes. What I figure was 60 years ago, right? Yes.
Exactly. Yeah, I'm saying even more exactly. It's the winter, 60 years ago winter, that I started working on things like the duality and subgradients of convex.
Yeah, and it's so beautiful.
Yeah, that's a lot of time.
So beautiful. Yeah.
Yeah. And it's been such a lot of pleasure. I have gotten so much fun and excitement of it. But one thing that we can understand as mathematicians, but many people are related to us and don't know mathematics, it's very hard for them to understand it, is that it's so beautiful. When things fit together, ideas. I love ideas. And then those are beautiful. And then ideas they reflect each other. And this idea has a reflection, and then there's another reflection, another. And it's like rainbows and rainbows of ideas. There's such beauty to this stuff. It's not just work and calculations and numbers as outsiders, mathematics.
And you say you got the inspiration from the beauty of the wildlife, right?
That's right. Somehow, there are many kinds of people. And in my case, yes, okay. There's another thing about mathematics which is extremely admirable. Truth. Say it's actually true or not true. Or some of the other things, well, it's somewhat not exactly true, and or you get something more true, even with COVID. What's true? True.
That's true.
But with mathematics, it's true or it isn't true, and then when it's true, it's beautiful.
Yeah.
And okay, so but you mentioned again the mountains. What I say. So this is my personality very much likes truth and beauty. I to focus on and knowing exact truth and the beauty of how things all fit together. And this is why I like to, there are many kinds of mathematicians too, and many of the ones that are most famous and win prizes and things like this are the ones who solve problems. Somebody had a problem in the past, some very famous problem nobody could solve, then you solve this problem, and that makes you famous. It's a big important challenge, but my kind of mathematics is different. My kind of mathematics is trying to organize ideas, discovering new ideas, organizing them all in a bigger pattern to be beautiful, true and beautiful and useful. That's a different kind of mathematics, but there are other people. We can think of others. And probability theory is Kolmogorov. Many places we can see people who produce something that organized rather than simply proved something.
Yeah. Yeah. We can see that you totally enjoy that. Solving puzzles.
Yes, and I hope to convey this to young people, because there's so much enjoyment in this. At least if once you find your way and you find that you can ask your own questions and discover answers,
Mhm.
then it can be so thrilling, so interesting to you.
Yeah.
All right, so Terry, can I ask you a technical question?
Well, okay, if it's
So,
simple.
For the okay, right, that's right. For the horizontal subgradient, can you explain more about the significance of the horizontal subgradient?
Yeah, so I'm glad you asked that because it seems very obscure to people at the beginning. But maybe we could, let's see, go back to it. Horizon subgradients. That's just a definition. Okay. Okay. And the picture shows that the horizontal subgradients, or horizontal normals to the epigraph. Now let's go back to understand this a little bit. Let's go back to convex analysis. So in convex analysis, these are simply the normal vectors to the domains. And you know that in convex analysis, we have many constraint qualifications. So there was the idea of the sum of the subgradients of the sum of two convex functions. So we have conditions of the sort that the relative interiors of the domains should have a non-empty intersection, or maybe or another version is that the interior of one domain should meet the other domain, and so forth. But what those things mean, those conditions mean, is that those two convex sets cannot be separated. Those relative interior conditions are exactly like the two convex sets cannot be separated. But that means that there is no normal vector to one that is a negative normal vector to the other. So it exactly corresponds to that kind of constraint qualification that we saw down here in this in this theorem. There should be no non-zero. Now if these were convex functions, then I'd be talking here about the normal cone to C1 at X, the set C1 at X. There should be no vector in the normal cone to C1 at this. Remember, X is in the intersection of the two sets. There should be no normal vector to the one whose opposite is in the normal cone to the set C2, because that would mean that this vector V would define a separating hyperplane there. So sets shouldn't be separated. And so that's the nature of the constraint qualification. But now that we want to deal with functions that aren't just convex functions, we can't just rely on the convex sets that are the effective domains of the functions, because what's really important is this condition in the of what's normal to the epigraph. But still the same rule comes in. So this is just like the variational analysis version of a separation condition. In fact, we can, Boris Mordovich knows this very well too. You can define generalized separation and so forth in terms of these normal cone conditions for sets. And that's a nice thing to do. Without using these horizon subgradients, we would not have the calculus, because the calculus requires the constraint qualifications. And on the other hand, though, these aren't useful unless you could calculate them at the same time. And that's why, although I didn't write it here, I wanted to emphasize that this same condition, I'll just have to say it, the same condition implies that the horizon subgradient set is included in the sum of the horizon subgradient sets. In other words, we get an estimate, and then there's an equation if we have the regularity. So this the same kind of calculus then gives us calculus of this, and thereby gives us a calculus that we can use in constraint qualifications. So there's another, this Lagrange multiplier one had another constraint qualification. And although in this case, well, I don't know, I'm saying too much. I hope that answers your question.
That's good, Terry. So how about the history of introducing this concept? when and how it was started with. Yeah.
Horizon subgradients?
Yeah, the horizontal subgradient.
Yeah, we did not actually introduce them in the beginning because in the convex analysis book, well, what's the beginning? In convex analysis, at the time of my convex analysis book, it was enough just to talk about normal cones to the domains. And in fact, that book does not really say much about normal cones. The normal cones are the subgradients of the indicator functions. And as I say, the constraint qualifications are expressed by non-separation conditions instead of by normal vectors. But then when we started to go into the variational analysis, in the first stage, when I was working with Clark, we were making everything be convex. And there again, somehow you didn't need it quite so completely, although I guess we did anyway. We still, even in that subject, we had the horizon subgradients because you still needed that for the constraint qualifications to get a calculus. But one of the reasons I realized that the convexification had to be abandoned, it was because you could get better calculus results in the way that Mortovich had found, and then you have to make the horizon subgradients more and more explicit. They are not simply what they were earlier was the horizon subgradients are the recession vectors of the convex set of subgradients. Maybe that's the way to say it. So the set of subgradients was convex, and if it's unbounded if and only if it had some recession vectors. And the horizon subgradients were those recession vectors. But once we get rid of the convexification, we can't rely on just recession vectors. And by the way, I have a different meaning for that now, the more general meaning for recession vector. So we need to make them explicit and work with them and their calculus directly.
Okay, thank you, Terry. I only would want to know the origin of mathematics, right? Not only correctness, but also the history. Thank you very much.
I think it's very important to everybody because it helps explain how ideas develop and how many people often have similar ideas at the same time and where they come from, why these ideas are important. And people who cut themselves off from it will probably not do good research. You should understand how other people think and how things happen.
Yeah, thank you.
Are there any questions from the participants?
Hello, Professor. Can I ask a question?
Sure.
Because just like the Professor Song asked a question, in your convex analysis, you define as the normal cone to the domain is the recession cone of the subgradient. So I want to ask, what's the relationship between the recession cone and the horizon cone? Because they have the different meaning.
Yes, that's a good thing to ask. But in the convex analysis, the recession cone, what's called the recession cone there and the horizon cone are the same thing. But otherwise, they're not necessarily the same thing. And so you're just, I don't have an example to show you a picture of, but they're not. But what the horizon cone explains, this brings in a subject I'm not talking about in these lectures, so I think it's very important for understanding. It's understanding how sequences, how unbounded sequences can converge to a limit. Unbounded sequences converge to a limit that isn't an ordinary point, but is instead what I call a horizon point. So what's explained in that chapter 3 of the variational analysis book is that you can make a compactification of Rn by basically adding a horizon, a point in the sky in every possible direction, horizon points. And then if you want to look at a closed set that isn't, you can look at, you can take for any unbounded set, you can look at all the limits of that set that are horizon points, that is limits of unbounded sequences in that set. And then those horizon points can be represented by rays that point in the direction in question. And so the horizon cone of a set is the set of rays that point in the directions in which unbounded sequences in that set can converge to direction points on the horizon. So in the case of a convex set, all these points, you can go, any unbounded, you can go in a straight line to any of these, more or less all these points. So the points, the points, the direction points that are associated in the sky, the celestial spheres, I call it, with the cosmic space, with the convex set are just correspond to the classical recession cone. But if they're non-convex set, they're something different, and they correspond. You need a more general definition, and you get the horizon cone. But the variational analysis book extends the idea of a recession cone in a different way. The idea of a recession cone for a convex set was certain ways in which the set could move, or certain ways in which you could always move into the set from every possible point into the set. And so there's a local version of that. What are the kind of, you have a non-convex set, which maybe has a boundary and an interior, and what, there are some kind of places, directions, local directions in which you can uniformly move without leaving the set. And so there's a direction of that called horizon. There's a horizon cone to find that. It's a pretty interesting concept, and it has a number of applications, but I won't be describing it in this talk. But again, it all has to do with how to understand unboundedness and convergence of unbounded sequences.
Thanks for your nice answer.
Okay.
Terry, you have a question. What about the proximal subgradient and the proximal normal cone?
Yes, this is a very good question, Jane. Thank you, because I said a little bit about it, but not enough in the last talk. So, which is about variational geometry. So maybe the best way to think about it is first to describe it again in the variational geometry. So we can have a proximal normal to a set, a proximal normal to a closed set. So proximal normal is a normal that is derivable from some projection of a point onto that set. It's a point where some small Euclidean ball could touch the set, and that's a very useful idea to have in many ways, and you can use it to develop a lot of concepts, but it's somehow an intermediate concept. And why is that? Because it's inherently a second order concept. It depends on having a quadratic function. And you can immediately see that something could be different and it depends on the existence of projections. Nearest points, so on local compactness. So you can immediately see that, for instance, you want to go to infinite dimensional spaces, you don't have local compactness, you can't use projections. So horizon, so the proximal normals are already going to be a problem, even in an infinite dimension Hilbert space with generalization. But there's something more fundamental about it, which impressed me a lot. Well, for one thing, the proximal cone of proximal normals isn't even closed necessarily. And but then as I say, okay, so what was fundamental? So in my last lecture, I showed that the regular normals are exactly the vectors that you can get as the gradients at that point of a C1 function that has its local maximum at that point. You can even make it be the global maximum. So they correspond to maximizing a C1 function. But there's a similar result for proximal normals. Proximal normals are just the things you could get by maximizing a C2 function. So again, it depends on second order differentiability. So So for my philosophy, what I'm first going to do is develop a first order theory of variational geometry. Then I will go on to a second order theory. So it seems to me a false step to try to develop a first order theory of variational geometry using a second order concept that depends on C2 functions instead of C1 functions. And anyway, with the variational geometry, we have this wonderful relationship, polarity relationship between the regular ones and the tangent ones and so forth. There is no such thing with proximal normals and subgradients. Proximal things are just an auxiliary concept that is technically helpful, but it should not be the fundamental concept in my view. But this is, by the way, as you know, where I broke away from Francis Clark, who always wanted to stick to the proximal normals. And I'm explaining my philosophy of why we started to go down different paths at that point after being very close working together for so many years, because I don't know, maybe he felt himself too much tied up in his definitions of proximal normals and convexification of normals and things like that. Then when you come to functions, well, it's more or less the same thing for functions. You can use it for a lot of calculations, but it's a second concept. And more recently, I've been working on things like variational convexity and no, I've been working. No, take it back. I'm working on things about the proximal normal, augmented Lagrangians, and how to make things converge with the augmented Lagrangian method, and all this involves proximal stuff, and it's basically limited in practice to finite dimensions because proximal don't. I'm saying too much again, but there are very solid reasons for why I pushed proximal normals to the side and went with general ones, regular ones.
Mm-hmm. Yeah, seems we don't need it so much, right?
Well, you can use it. It's just not the fundamental idea for which to build anything. That's all. I think proximal normals are definitely useful in many ways, and Clark has shown it, especially in some of his work in control theory. He uses it as a technique. Well, what should the basic idea be of a first order subject should have first order concepts in the basic idea, is my philosophy. And anyway, the relationships are much better if you take this more general approach. It's not even true that the regular normal cone is the closure of the proximal normal cone. That isn't even true.
Mm.
The proximal normal cone is subcone of the regular normal cone.
Yeah. Any more questions? Okay, I'll read a question. Okay, in the current slide, the traditional outlook tries to eliminate false candidate, while the modern one tries to find numerical methods. I think the change is because the existence of computation tools, computer. Do you think the change of computation tools will promote the evolution of theory?
Yes, that's a good question. I absolutely agree with it, although I perhaps would say it in a slightly different way. Because you could say that in both cases, the classical and the modern, it was a sort of computational tool. The whole thing was because in the traditional case, you're dealing, say, with a one-dimensional, two-dimensional problem. And first, you will compute all of the points satisfying where the gradient is zero or the derivative is zero. So you will compute those, but you compute those using the calculus and using closed form formulas that we have out of the calculus. You don't compute it numerically. You compute it in closed form. So computation was important in both cases. Now in the modern outlook, computation is still important, but we have a computer. Okay, but computer tool, I am not exactly sure what I want to say about a computer tool. A computer tool is that the hard drive, it's the screen of the computer. I think what's meant by a computer tool is the mathematics of numerical algorithms, but that's part of the same subject. It isn't that we already have the existence of algorithms, and then therefore we have a different outlook. It's that we have problems. The existence of computers opened up kinds of problems that were very different. Classically, you just could look at some 2 or 3 dimensional problem, or you could just make some theoretical assertion about the calculus of variations. But in the modern terms, we're looking at problems that are very, very complicated with many kind of constraints and so forth. And how are we going to do this? We have no hope. So what we need is a way of computing both the first and second order conditions at the same time, so to speak. I mean, we can't first compute. This never happens, we all know quite a bit about numerical methodology and optimization. There's no method that first computes a solution that satisfies the gradient equals 0 and then does something with second order things. They all find the point at the same time, using the fact that the goal is to find a point with gradient 0 and that may satisfy some second order conditions. And it's that information, it's not that we already have tools in the forms of algorithms to do it, it's the fact that the computer allows us to use our mathematics to design tools to do that, in which we do it all at once, first and second order conditions at once. Not a two-stage process as classically. I hope that answers the question. I think this is very important in the whole outlook here. We are very, very influenced by the existence of computers. It created this whole subject. Nobody would be thinking about these problems in any practical sense, and they wouldn't even bother. All these problems with a million constraints and a million dimensions of unknowns, who would be thinking about them unless they were important practically? And they would never be important practically without computers.
Thank you, he said. So Terry, will you explain more on the modern outlook in the next 2 lectures?
Yes, there certainly will be many things about this, including, I remember very well the question yesterday about, is variational analysis good for anything in optimization? Mm-hmm. And I didn't have a full answer then, but you'll see a lot. One of the ideas of variational analysis is that you can that it's used to justify algorithms. So all right, so this fits in with this modern outlook again. So what we have to have are numerical methods that will find a locally optimal solution, or hopefully a globally optimal solution, but that gets us into a different type of a topic. But I'm just concerned here with locally optimal solutions. How will we find a locally optimal solution? Mm-hmm. So to use a lot of mathematics to describe what we mean by this locally optimal solution. And then we want to, like optimality conditions of one kind or another. And then we design the solution method on the basis of these optimality conditions. So we don't even have, we can't even think about a method until we understand these conditions. They're important to the whole design of a method. I mean, some of them are very, very sophisticated. For example, augmented Lagrangian methods are extremely sophisticated idea of how you're going to find a solution to a problem and why does it work? Variational analysis is essential to understanding all of that, but also Newton-like methods, and then there are all kinds of ones like solving problems I haven't been able to describe yet exactly, but variational inequality problems. There's so many more problems, and even to describe the problems, people couldn't describe them before. They're based on variational analysis. And then the characteristics of these problems involve variational analysis. And then when you do numerical methods, you also are very much occupied with the concept of error. There are errors, and have to show that the errors can be controlled. And how are they controlled? They are controlled by some kind of local properties or global properties, not just Lipschitz continuity, or things like that. And this will come especially in the last of my lectures. I will be talking about things like that. How can you make approximations? So one of the big triumphs of the theory, it wasn't called variational analysis quite then, but back quite a long time ago, in the 1980s, I think, was when Stephen Robinson justified numerical methods in classical nonlinear programming. He took classical nonlinear programming with equality, inequality constraints, and he justified certain numerical methods by using estimates that essentially amounted to an implicit function theorem that wasn't just the classical implicit function theorem, but worked for the solution of the Karush-Kuhn-Tucker conditions in nonlinear programming. I'll be talking about that in my fifth lecture. So we have a huge fundamental contribution to mathematics, implicit mapping theorems for solution mappings that aren't just given by equations, but by other things. And so where does that play into numerical methodology? You have to use that to justify the method. So for numerical methodology, the modern outlook involves two things. One is presenting the form of the, first of all, how to formulate the problem well, how to understand and formulate the problem. Not everybody writes the problem down in the right way at the beginning, or there are different ways to write it down, and some are better than others. We all know that from every kind of applied mathematics. But variational analysis has to guide you, and convexity, what is convex, guide you with how to formulate the problem. Next, you have to know how to reveal the target. You have to say, what are the conditions you're trying to solve? For example, local optimality conditions on the first order, you could write down the Karush-Kuhn-Tucker conditions, and then you could design an algorithm just to solve those conditions. But maybe there's something else with second order properties, like you have second order, then you could use some Newton method because you understand the second order conditions. But the important thing here is we're not just looking at classical nonlinear programming or some area where usual calculus more or less works. We get into far more general situations where we need something more. And anyway, variational analysis is what helps with all of that. And there's so much more to do with it, especially, I don't know, things like stochastic problems, probability theory. I could go on.
Thank you, Terry. Any more questions? If not, I think it's close to the time.
Okay.
For our dinner.
All right. I see, even if in the other two times, I didn't understand the lecture could be shorter. So try to fill
Oh,
it.
wait, there's a
I don't
question.
fill the time, you try to fill it.
Terry, there's a question. Can
Oh,
the
there's another question?
second, yeah, can the second order variation analysis help to characterize the local mean of the non-convex problem?
Absolutely right. Absolutely, that's the whole goal of it. That's exactly the whole goal of it. That's a good question. That's exactly what we're trying to do. But it's a non-convex problem that could be in a very general way. So look at this slide again. So of course, it could be much more special. You have to remember that when that I can take a very general problem and write it in the form of just minimizing a function over Rn, where this function is only lower semi-continuous, not even continuous necessarily. But it may have structure, but we'll worry about the structure later. But at this level, we have the first order condition. And then the question is this, exactly what I wanted to say in this thing. What about second order conditions? So second order variational analysis is going to try to help with this, but what is it we want to do? And so I try to explain here that the characterization it has to be one that helps. What kind of help will it provide? And these are the ingredients we will later use. We have second order subderivatives, graphical derivatives, local monotonicity properties, but there are also things like augmented Lagrangians that can come into all of this. But the whole idea is to use variational analysis is not just to be used, it's to be developed for this purpose. The purpose of variational analysis is to help with such things in optimization as giving you a kind of second order theory of a local minimum, a sufficient condition for a local minimum that will promote numerical methods.
Yeah.
And I will be talking about all of that,
Mm-hmm.
both tomorrow and the next day.
Yeah,
At the
that'd be
end.
great. Yeah.
Yeah.
Okay, so I think we can end now.
All right. Thank you very much, Jane.
Thank you,
So-
Terry.